Well, hello and welcome again to our journey into number theory, and we're up to looking at the law of quadratic reciprocity, which I stated in the previous video and did an example of. So just to remind you again, it says you start off with P and Q to be odd primes, and then the theorem says, this famous theorem of Gauss, that if either P or Q are 1 mod 4 primes, then the P is a square mod Q implies Q is a square mod P. And if they're both 3 mod 4 primes, then P is a square mod Q implies Q is not a square mod P. And we can combine all these together, in fact, by this rather cute little formula here, that P over Q is Q over P times minus 1 to this power. And that's the form we're going to use. That's the form we're going to aim for in our proof of the quadratic reciprocity theorem. And as I mentioned before, there are many proofs of this. Gauss gave lots of different proofs of this one, and there's a very cute one that just uses characters. It comes out in a few lines and things called Gauss sums, which actually goes back to Gauss himself. But the proof here I'm going to do is the one that's in most textbooks. I think it's the one due to Eisenstein. And it attracted Gauss's high approval. Because I think perhaps it was a bit of a backhanded compliment to himself, because he was so impressed with Eisenstein being able to give a better proof than Gauss himself did, that he regarded Eisenstein as one of the greatest mathematicians of all time, which is probably a little bit of an overstatement. Okay, so to do this we need a little lemma. And the lemma says let A be an odd is important here, an odd integer, and Q is a prime, P is a prime not dividing A. Then we take this funny number M, which is formed by you divide A by P and take the floor. That means you take if this this won't be an integer, so you take the next integer just below A over P. You do the same for 2a, divide it by p, take the integer just below, and so on all the way up to a half p minus 1 times a divided by p. So you take this funny number, and then the Legendre symbol a over p turns out to be minus 1 to just this number. Now you'll see where this is coming from when we look at the proof of this. So here's the proof. We're going to simply apply Gauss's lemma in the usual way as we've done before. So we start off with the set a, 2a up to a half p minus 1 times a. Now of course what we need to do is we need to take this set and we need to reduce it modulo p. That is, I need to divide each of these numbers by p, and then just look at the remainders, and then I'm going to count how many of the remainders are bigger than p minus 1 over 2. So that's what I'm doing here, and you can see, well, once I've done this, you can see where this is coming from. So you take a, you divide it by p, take the floor and multiply by p, and then you get the remainder. So this is just really dividing, it's doing the division algorithm on a and p. And then you do the same for 2a, you divide that by p, take the floor, multiply by p, you'll get a remainder. These remainders, of course, will be between, well, they can't be naught because p, this is not going to be an integer, so you'll get remainders here, but these will all be between 0 and p minus 1. And finally you do the same to the last element of the set, which is this one, and you get this here. Now what we then do is we're going to add both sides of these equations. Now if you add the left hand side, what you take out a factor of a, you're just adding up 1 plus 2 plus 3 up to a half p minus 1, and I'll leave you to do a little side calculation to convince yourself that that just adds up to a 1/8 p squared minus 1. You should know how to sum the numbers from 1 up to n. Is a half n plus 1, and if you replace the n with this and simplify, that's what you get. Now on the other hand, you're going to get the p into the sum of all these numbers, and these numbers we called m, you'll recall. So that was this funny number m that we had in our lemma. So I get p times m plus I get all the remainders. Now of course what we're interested in is how many of these remainders are bigger than p minus 1 over 2, because that number, which we called k, is the k from Gauss's lemma. So that's the next part of the proof. So these remainders now are all different. The remainders are all different since p doesn't divide a, and as in the proof of Gauss's lemma, I'm going to let a1 up to ak be those r's, those remainders that are bigger than a half p minus 1. So I'm going to relabel the r's in terms of a's. These ones are bigger than a half p minus 1, and the rest of the numbers, the rest of the r's, I'm going to relabel using that notation. So we're going to write the above statement we just had as a half, so what 1/8 p squared minus 1a is pm plus, and I can replace all the r's now by these a's. So this lot are the ones that are bigger than a half p minus 1, and this lot are the ones that are less than. Now, as we did before, when we did an example, when we did the proof of Gauss's lemma, I take p minus each of these numbers. So I take p minus each of these numbers, and that means these will all be less than a half p minus 1. And so now if I replace these with these, and then copy down the remaining ones up to here, then these numbers in some order will be distinct, and they're all less than, there are half p minus 1 of them, and they're all less than a half or equal to a half p minus 1, and so these are just the numbers from 1 up to a half p minus 1 in some order. So again, we're going to add these together, and of course again if you add these you can show that that's equal to that, as we saw before. And then I'm going to add these, and that gives me k lots of p, and then I have minus, I get the a1s up to ak's, and then I get the other mess, the other bit at the end, the ones that we started off with being less than a half p minus 1. Now, for the key step, we're going to subtract this equation from this one up here. Now, when we subtract, we're going to get a common factor of 1/8 p minus 1/8 p squared minus 1, but I'll get an a minus 1 there. I'm going to get a p times into m minus k there. And when I subtract, I'm going to get two lots of these ones. So I'm getting rid of all those will cancel, and I will get that minus that gives me two lots of these. Now at this point, you stand back and you just think about what you can get out of this rather strange looking equation here. Now we said at the beginning that a was an odd number. So 1/8 p squared minus 1, that is an integer, that's a whole number. You should convince yourself that p minus 1 and p plus 1 have a factor of 8, and so that's a whole number. Now if a is odd, a minus 1 is even, so that is an even number. That is an even number. P is odd, so m minus k is an even number. Now if you've got a difference of two numbers is even, then these m and k must have the same parity. Either they're both even or they're both odd, in order for their difference to be even. And that means then that minus 1, if they're both even, then minus 1 to the k and minus 1 to the m are both equal to 1. And if they're both odd, then minus 1 to the k and minus 1 to the m are both equal to minus 1. So in either case, these are equal to each other. And then Gauss's lemma says that a over p is minus 1 to the k, but minus 1 to the k is minus 1 to the m, and that is what we had to get. So the Legendre symbol a over p now is minus 1 to this m, which was that funny number we constructed at the beginning as the floor of a over p plus the floor of 2a over p, and so on. So our aim now is to finish off the proof of the reciprocity theorem, and to do that we're going to simply interpret what we've just done. So now I'm going to firstly replace A with Q. So A just had to be odd. Now I'm replacing it with Q, an odd prime. And then our M simply looked like that from the previous work. And then I'm going to interchange the two, and I'm now going to interchange the P and the Q and do exactly the same thing, and I'm going to call that N. So by this lemma that we've just proven, we've proven that P over Q was minus 1 to the M, and Q over P was minus 1 to the N. And so I can multiply these together and arrive at that. Now remember, what we're aiming to do is we need to show now that this M plus N is in fact just this thing, a half P minus 1, a half Q minus 1, and that gets us the proof of the reciprocity theorem. To do that, we just look at some geometry here. We draw a rectangle with vertices 0, 0, 0, P over 2, P over 2, Q over 2, 0, Q over 2, and I'm going to join the diagonal through here and consider this rectangle. And we're going to try and connect this sum here, to begin with at least, this sum here with my picture. Now firstly note that the rectangle contains a half P minus 1, a half Q minus 1 lattice points, that is points with integer coordinates excluding the boundary. That should be easy to see because this will not be a whole number. The next lattice point inside the rectangle here will be P minus 1 over 2, Q minus 1 over 2, and then we can just multiply those to get the number of lattice points inside, excluding the boundary. Now the diagonal from here, which simple geometry, simple algebra shows, is given by the equation y is P over Q times x. And so that means then, if I now pick any number n along here, if we concentrate on this part of the triangle firstly, if I take any number n, then the number of lattice points will be the y value here, which is nq over p, and I take the floor of that. That'll be the number of lattice points lying on each one of these lines for any given n that lie on or below the diagonal. And so if I add all those up, if I add up all of these values where n goes from 1, 2, 3 up to p minus 1 over 2, that of course will get me my m. Now there are no lattice points on the diagonal because p is prime, so p can't cancel with any, this x is less than p over 2, and so if p is a prime, it can't cancel with any integer less than p over 2. So that means this m is counting all the lattice points that are below this diagonal, in other words inside this triangle. So this m is counting all the lattice points inside the triangle. There are none on the diagonal, and we know that the sum of these as n varies gives us my m, and that gives me all the lattice points in the triangle. Now you can do exactly the same argument on the n, and the n is, looking at it from this angle, the number of lattice points in here is going to be given by n. So n counts all the lattice points above the diagonal to the right of the y-axis, so in other words in this triangle. Finally then, n plus m gives you all the lattice points in the rectangle, but we agreed before that that was just a half p minus 1, a half q minus 1. And that completes the proof, or a proof, of the reciprocity theorem. It is an elegant proof, and one that goes back to Eisenstein. You might like to look up some other proofs of this celebrated result. So a little example I think probably is in order at this point. So we're going to show that 5 is a quadratic residue for any prime that's of the shape plus or minus 1 mod 10. So again, we're seeing the primes splitting up into various different modulus classes. So the plus or minus 1 mod 10s, these have the following, well, 5 is a square for those ones. So here's a little, here. So to check whether 5, so we're taking P to be a prime of the form 10k plus 1 or 10k minus 1, so it's either a plus or minus 1 mod 10 prime, and we want to see whether 5 is a square. So you simply look at the Legendre symbol. Now 5 is a 1 mod 4 prime, so you can turn this upside down, and then you can simply read the top now modulo 5, so that disappears. You just get plus or minus 1. Now if it's plus 1, then you get 1. And we've seen before that because 5 is a 1 mod 4 prime, minus 1 is a square. So in both cases we get 1. And that means 5 is a quadratic residue. So 5 is a prime, is a square, I should say, for all primes of the form P plus or minus 1 mod 10. Slightly more interesting example is to find all the primes for which 3 is a square modulo P. That is interesting. For what primes is 3 always a square? And you'll see that this is actually quite easy to do. Now that we have this beautiful reciprocity theorem, this is really quite easy. So firstly, let me suppose that 3 is a square modulo P. Now, because 3 is a 3 mod 4 prime, we have to look at two cases, because it's going to depend on whether this P is a 1 mod 4 prime, in which case we can invert the Legendre symbol, and if it's a 3 mod 4 prime, then we'll pick up a minus 1. So if P is a 1 mod 4 prime, then I can just quickly flip these upside down. And now Euler says, this is using Euler, says that this is congruent to P to the 3 minus 1 over 2, but that's just P modulo 3. So I can use Euler's formula at this point, and 3 minus 1 over 2 is just 1, so this is just 3 over P is just congruent to P mod 3. And remember, we assumed that this was 1. So now I have P is congruent to 1 mod 3, and so this is congruent to 1. So P is a 1 mod 3 prime, and P is a 1 mod 4 prime, and I leave you to check from Chinese remainder. You can glue these together. P's got to be a 1 mod 12 prime. So I've simply used the Chinese remainder theorem there to glue the two together. So that means if 3 is a square mod P is a 1 mod 4 prime, then P has to be 1 mod 12. Now if P is a minus 1 mod 4, that is a 3 mod 4 prime or a minus 1 mod 4 prime, then I can flip these across, but now I've got 2 mod 3 or minus 1, 3 mod 4s or minus 1 mod 4 prime, so when I flip it I get a minus. And then I do the same thing. This by Euler is congruent to that, and that means then that this is now, so this, remember, was congruent to minus 1, and that means that P is a minus 1 mod 4 prime, and from this one we get P as a minus 1 mod 12 prime. And if you glue these two together, then you get P is a minus 1 mod 12 prime. Sorry, this was plus 1. I'm sorry for that. This was our assumption our assumption up here was this was 1. So this tells me that P is a minus 3 mod 3 prime. And so when you glue this one together with this one, you get p is a minus 1 mod 12 prime. So that means if 3 is a square modulo p, then the p has to be a, then that implies that p is a plus or minus 1 mod 12 prime. Now the converse is also true. I'll leave you to check that if p is a plus or minus 1 mod 12 prime, then 3 over p is 1. And so we can see how this works here. Final example of this one is to have a look at, we're going to show that this is a nice application here. We're going to show that this Diophantine equation, and I've got too many ones there I think, this should have been just I think 113. We're going to show that this Diophantine equation, 113 x squared minus y squared is 43, has no integer solutions. That is, there are no integers x and y, so that 113 times x squared minus any other square ever gives you 43. So you can use this quadratic reciprocity ideas to examine Diophantine equations, at least at the moment ones involving squares. So here's a little, you'll see how simple it is to prove this. This is quite lovely if you think about, if I just gave you that bare hands and said show that there are no numbers that make this work, might take a little bit of work to actually show this, especially if the numbers here are large. So suppose there are integers that make this true. So then I put on my mod 113 glasses and I read this modulo 113, so that disappears, and I can take the minus on the other side, and that would say y squared is congruent to minus 43 mod 113. That is, minus 43 is claimed to be a square modulo 113. However, if I now look at the Legendre symbol, minus 43 on 113, then I can flip this upside down. Now 43 is a 3 mod 4 prime, and 113 is also a, no, that's not quite right, is it? This one here, what's 113? So 1112. Well, I'll have to leave you to check this. When you flip it upside down, you end up with 113 on 44. There. So 113, let me just do a little calculation here. 113 is equal to 4 times 20, so that's 28 plus 1, isn't it? So this is going to be a 1 mod 4 prime. So I can flip this upside down without changing the sign, but I've got a minus 1 here, and we're going to end up with 113 on 43. Now when I read this one mod 43, I get 27, and then when I simplify this, I can take out a 9 out of this. This is 9 times 3, and 9 is a square, so that goes, and I just get 3 on 43. These are both 3 mod 4 primes, so when you flip it you get a negative. And now if I read this modulo 3, I get 1, and 1 is a square, and so I've just got a minus 1 there. And that means that means that the Legendre symbol is minus 1, which tells me that minus 43 is not a square mod 113, and that is a contradiction to this line here. And so there's a nice little application of the quadratic reciprocity theorem.